So this second clip on radiation is going to look at radioactive half-life, which is quite a hard concept to consider, not least because we're used to two halves making a whole, but in this case it's not strictly true. If we take any radioactive material, say we've got 200 grams of this particular material and it's radioactive, so it's emitting radiation. Doesn't really matter which kind, alpha, beta or gamma. What's happening is that the radioactive atoms are changing inside it from one form to another. So after a particular amount of time, half of those radioactive atoms will have decayed or changed into something else. And that amount of time is called one half-life. So we've now only got 100 grams of radioactive material left. The other atoms have changed into something else. They may well have changed into a gas and disappeared, or they may have changed into another solid and still be present. But we have only 100 grams of radioactive material left, as opposed to 200 grams at the beginning. And that's taken one half-life. That also means that the amount of radiation being given off will have halved. Okay, so now we've only got half as much radiation being given off. And that's the other definition for a half-life. It's the amount of time it takes for the amount of radiation being given off by a material to halve, or the number of atoms to halve. If we wait another half-life, however, and this is what confuses a fair number of people, so watch out, another half-life, so now we've done 2. Instead of all of it being gone, all that's happened is that we are now left with half of what we had before. So 50 grams. Because there was only half as many atoms there, half of them decayed in half-life, and therefore the amount of radiation will also have halved. We do it again, I'm sure you can guess. We're left with half of what we had, 25 grams, and a tiny amount of radiation being given off. Okay. Now, whether we graph the mass that we've got left or the amount of radiation being given off, either way, we finish up with a graph that looks like this. Over time, so we might have radiation, or we might have mass remaining. Either way, it looks like this. It starts off going down very quickly, because we started off with 200 grams, and then we had 100 grams, and then we had 50 grams, and then we had 25 grams, and so on and so on. Or we started off with 4 wavy lines of radiation, then 2, then 1, then a half. But each one of these points where it's halved is a half-life. So if you have a graph of radiation or the mass remaining, then you can find the half-life by the time it takes for the radiation or the mass to halve. So if you start off with 200, here you're looking for the point where you're down to 100. Or if you start off with 100, you're looking at the point where you're down to 50, and so on. And that also means that this sort of goes on forever, because we would go from 25 to 12.5, and then 6 1/4, and 3 1/8, and so on. But when you get down to a very low level of radiation coming off a particular material, it just gets lost in what we call the background radiation, which is all the radiation being given off by atoms that are radioactive in our rocks, in our food, in our atmosphere, and the occasional one given off by medical work or a nuclear power station, and ones coming from space as well. So after a while you can't really tell.